In the unending quiet between the stars, there is a darkness more profound than any night humanity has ever known. It is a cold, patient emptiness, punctuated only by the distant glitter of suns that will live and die without witness. Through this immense interstellar gulf, silent travelers drift. They are fragments of other worlds, debris from cosmic collisions, the orphaned children of long-dead stars. For eons they wander following paths, dictated by the invisible currents of gravity, their journeys spanning gulfs of time and space that defy human comprehension. We have always looked up and wondered if we are alone. We built monuments to the stars, crafted myths from their movements, and eventually turned lenses of glass and silicon towards them, listening for a signal, a sign, a whisper across the void. But perhaps the messages have been arriving all along, not as radio waves, but as physical relics, silent and unannounced. On the digital frontier of modern astronomy, our new eyes are not human. They are robotic observatories, tireless sentinels that scan the heavens, cataloguing millions of points of light every single night. They hunt for the subtle changes in the celestial tapestry, the faint motion of a killer asteroid, the flicker of a distant supernova. And in this deluge of data, among the countless known and categorized objects, an algorithm sometimes flags an anomaly. A ghost. A smudge of pixels moving in a way it should not. This is how the story of GB00810 begins. Not with a thunderous roar, but with a quiet query in a server farm, a whisper of something new, something strange, something other. The initial calculations were electrifying, suggesting a trajectory so extreme, so open, that it seemed impossible for it to belong to our Sunday. The news spread through the astronomical community like a shockwave. After centuries of gazing outward, had the outside finally truly come to visit us again? The hunt was on for a traveller that might be a sibling to a legend, a faint spectre that could rewrite our understanding of the cosmic neighbourhood. To grasp the magnitude of this potential discovery, we must first journey back to the moment our conception of the solar system as a closed, isolated family was irrevocably shattered. For most of history, we believed our celestial home was an island universe. The planets, the asteroids, the comets, all were bound to our sun, circling in a predictable gravitational dance. Then, in 2017, an object of profound strangeness swept through our midst. It was discovered by the Pan-STARRS telescope in Hawaii, a faint streak of light moving with astonishing speed, designated 1I 2017 U1. It was later given a Hawaiian name, Oumuamua, meaning a messenger from afar arriving first. The name was an understatement. Oumuamua was not just from afar, it was from another star system entirely. Its trajectory was a hyperbola, a path so sharply bent and so fast that our sun's gravity was little more than a temporary inconvenience. It was not orbiting, it was merely passing through a tourist on a cosmic scale. But its strangeness had only just begun. As astronomers frantically trained every available telescope on the visitor, the mystery deepened. Oumuamua was small, dark and reddish, likely elongated, perhaps shaped like a cosmic cigar or a flattened pancake. Most baffling of all, it displayed no cometary activity. There was no coma, the beautiful halo of gas and dust that envelops a comet's nucleus as it is warmed by the sunday. It was a bare, inert rock, or so it seemed, and yet it was accelerating. After it slingshotted around the sun, it began to speed up, pushed by a gentle, persistent force that gravity alone could not explain. This non-gravitational acceleration is common in comets. The sublimation of ice on their sunlit side acts like a series of tiny rocket thrusters, giving them a little extra push. But Oumuamua had no visible jets, no tail, no coma. So what was pushing it? The scientific community erupted with theories. Perhaps it was an object made of solid hydrogen, evaporating invisibly. Maybe it was an impossibly porous cosmic dust bunny, pushed by the subtle pressure of sunlight itself. Then came the most provocative hypothesis of all, championed by Harvard astronomer Avi Loeb. What if Oumuamua wasn't a natural object? What if its acceleration was caused by solar radiation pressure acting on an object that was very thin, very wide, and artificially made? A solar sail, a piece of alien technology tumbling silently through our solar system. The idea was met with immense skepticism, but it captured the public imagination and highlighted just how profoundly weird our first interstellar guest truly was. Oumuamua offered no easy answers. It departed as enigmatically as it arrived, leaving behind a trail of tantalizing questions and a fundamental shift in our perception. We were not alone. Our solar system was not an island. It was a port of call on an interstellar ocean. Just 2 years later, the ocean delivered another traveler. This one, however, was dramatically different. Discovered not by a professional survey but by an amateur astronomer in Crimea, Gennady Borisov, the object was quickly confirmed as interstellar. It was named 2I, Borisov, in his honor. Where Oumuamua was cryptic and inert, Borisov was gloriously, comfortingly familiar. It looked and acted exactly like a comet. It sported a magnificent coma and a long streaming tail of dust and gas. For the first time, we could perform detailed spectroscopy on material forged in another star system. It was like receiving a geological sample from an alien world delivered to our doorstep. The analysis revealed a composition that was both alien and recognizable. Borisov was rich in carbon monoxide, far more so than comets from our own system. This hinted that it was born in a much colder region of its home planetary system, perhaps around a red dwarf star. Yet in many other ways it was remarkably similar to our own comets. Water, cyanogen, diatomic carbon, the basic building blocks were all there. If Oumuamua was a cryptic telegram, Borisov was a friendly postcard. It told us that the processes that build comets, and by extension planets, might not be so different from one star to another. The galaxy, it seemed, used a similar recipe book. These two initial visitors established the breathtaking possibilities. One was a profound enigma that challenged our definitions of a natural object. The other was a reassuring affirmation of cosmic chemistry. They set the stage, creating an atmosphere of intense anticipation. Who would be the third visitor? What secrets would it carry? It was into this charged environment that the faint spectre of GB00810 emerged. The process of finding such an object is a modern miracle of data processing. Imagine a vast dark canvas stretching to infinity. Each night, a telescope takes a snapshot of a tiny patch of that canvas. Then it takes another and another. Software then meticulously compares these images, looking for anything that has moved. The overwhelming majority of these moving dots are known asteroids, familiar comets, or man-made satellites. They follow predictable paths confined to the gravitational basin of our Sunday. To understand the difference, picture a vast, shallow bowl. This bowl is our Sun's gravity well. Everything in our solar system, planets, asteroids, comets, is like a marble rolling around inside this bowl. Some roll in tight circles near the center like Earth. Others follow long, looping paths that take them far out to the rim before they inevitably fall back in like Halley's Comet. But they are all trapped. They lack the energy to escape the bowl. An interstellar object is entirely different. It is a marble that did not start inside the bowl. It comes screaming in from the outside, from some other region of the cosmic floor. It has so much velocity that the bowl's gentle slope can only slightly deflect its path. It will dip in curve around the center and then shoot right back out the other side, destined never to return. This escape velocity, this measure of an object's freedom from the sun, is the golden ticket. In astronomical terms, it's called hyperbolic excess velocity, or V infinity. If that value is significantly greater than 0, you have found a wanderer from the stars. When the first few observations of GB00810 were fed into the computers, the orbit solution that came out was wildly hyperbolic. The marble was not from our bowl. The V infinity value was high, placing it squarely in the same category as Oumuamua and Borisov. A third messenger had arrived. The initial thrill was immense, but it was tempered by extreme caution. The reason for this caution was the object's single most challenging characteristic, its faintness. GB00810 was astonishingly dim, a mere phantom on the edge of detectability. This faintness presented a colossal problem. Calculating an object's orbit is like a cosmic game of connect the dots. Each observation, a measurement of its position in the sky at a specific time, is one dot. The more dots you have and the more spread out they are over time, the more confidence you can have in the line you draw through them, which represents the object's path through space. This span of time is called the observational arc. With only a few dots clustered closely together, a short observational arc, your line is little more than a guess. A tiny error in the position of one dot can dramatically change the projected path, sending it careening off in a completely different direction. For the initial orbit of GB00810, the arc was perilously short. The dots were few and they were fuzzy. The claim of an interstellar origin was hanging by a thread of uncertain data. A race against time began. GB00810 was on its way out, growing fainter with each passing hour. Astronomers around the globe scrambled, pointing their most powerful instruments at that tiny patch of sky, desperate to collect more dots before the ghost vanished completely. Each new data point was fed into the models, refining the trajectory. The initial excitement gave way to a tense, methodical process of verification. It was a high-stakes celestial detective story. The clues were photons that had travelled for hundreds of millions of miles, collected by mirrors the size of living rooms. The detectives were astrophysicists, their interrogation tool a complex set of orbital mechanics equations, and the suspect was a silent, distant speck of ice and rock. Then, as the observational arc lengthened, a new narrative began to emerge. The trajectory started to change. The sharply angled, open-ended hyperbola began to soften, to bend. With each new data point, the calculated path curved a little more, pulling back from the freedom of interstellar space. The V-infinity value, once so impressively high, began to shrink. It crept closer and closer to zero. The marble, it seemed, might not escape the bowl after all. The dramatic conclusion was that GB00810 was not an alien visitor. It was an impostor, a native of our own solar system masquerading as an interstellar wanderer. The initial sense of disappointment was palpable. The third messenger was a false alarm. But this letdown quickly transformed into a different kind of fascination. For GB00810 was no ordinary comet. To mimic an interstellar trajectory so convincingly, it had to have come from the most remote, mysterious and unexplored region of our solar system, the Oort cloud. The Oort cloud is not a place you can see. It is a theoretical realm, a staggering concept born from the mind of Dutch astronomer Jan Oort in 1950. He was wrestling with a cometary puzzle. Some comets, known as long-period comets, travel on enormous orbits that take thousands or even millions of years to complete. Where did they come from? And why hadn't they all been exhausted over the age of the solar system, either thrown out into interstellar space or crashing into the sun? Oort's brilliant deduction was that our solar system possesses a vast, unseen reservoir of icy bodies, a colossal spherical shell surrounding us at an immense distance. To appreciate the scale of this structure is to confront the true emptiness of space. Imagine our solar system out to the orbit of Neptune as a small coin sitting in the center of a massive sports stadium. The Oort cloud would begin at the edge of the stadium's playing field and extend all the way out past the last row of seats and then far beyond into the surrounding city. It is 1,000 times farther from the Sun than Pluto. Its outer edge may reach halfway to the nearest star, Proxima Centauri. Within this unfathomable volume, perhaps 1 trillion cometary nuclei drift in a state of cosmic hibernation. They are the pristine leftover building materials from the formation of our solar system 4.6 billion years ago. These objects are only tenuously bound by the Sun's gravity. They move with glacial slowness, completing one orbit in millions of years. They are susceptible to the gentlest of nudges. The gravitational pull of a passing star, the tidal forces of the Milky Way galaxy itself, or a close encounter with another Oort cloud object can be enough to disrupt a comet's stable distant orbit. This tiny perturbation happening in the deep freeze of the outer dark can be a death sentence or a ticket to a new life. It can send the comet hurtling out into interstellar space, lost from our solar system forever. Or it can send it on the opposite path, a long, slow fall inward, a million-year journey towards the distant pinprick Sunday. This is the likely story of GB00810. It was what astronomers call a dynamically new comet, a first-time visitor from the Oort cloud. Think of it like dropping an object from an impossibly high tower. For its entire journey it is accelerating, By the time it reaches the ground, the inner solar system, it is moving at its maximum possible speed. This is why GB00810's orbit initially looked so hyperbolic. It was entering the planetary region with the highest velocity a native object can possess, pushing the very definition of being gravitationally bound. Its energy was so close to the escape threshold that our early fuzzy measurements mistakenly placed it on the other side of that line. GB00810 was not an alien but a deep country cousin we had never met, arriving from the forgotten frontier of our own home. The case of the Faint Impostor was closed, but in solving one mystery, it had illuminated a much deeper, more profound puzzle. The story of GB00810, the comet that cried Interstellar, was not a failure of science. It was a vital dress rehearsal. It demonstrated that our detection systems are now so sensitive that they are catching these borderline objects from the fringes of our own system. This forces us to refine our methods, to understand the subtle signatures that separate the fastest possible native from the slowest possible alien. But it also raised an unsettling question. If we can be fooled by a faint imposter like this, how many true times interstellar objects are we missing? Oumuamua was discovered because it was relatively close and reflective. Borisov was found because it was large and active, producing a bright coma. What if the galaxy is teeming with travelers that are small, dark and inert, objects like Oumuamua but farther away or made of non-reflective materials? Our current surveys would be completely blind to them. We might be standing on the shore of a cosmic ocean noticing only the largest, brightest ships, while a fleet of smaller, darker vessels slips by completely unseen. The puzzle deepens. We have two confirmed data points, Oumuamua and Borisov. One was a bizarre rocky anomaly. The other, a comfortingly familiar comet. This is where the second half of our title comes into play, Borisov's hidden twin. What if GB00810 had times been interstellar? What if it had been another object just like Two-Eye Borisov? The discovery of a second Borisov-like comet would have been a scientific bombshell. It would powerfully suggest that the type of comet Borisov represents is not a fluke, but is perhaps a common, even dominant type of object in our galaxy. Its high carbon monoxide content, which pointed to formation in a very cold environment, might be the standard recipe for comets around other stars. This has staggering implications for the prevalence of life. Comets are thought to have been crucial delivery vehicles seeding the early Earth with water and the organic molecules necessary for life to begin. If comets like Borisov are common, then it suggests that the chemical ingredients for life and the means to deliver them to young rocky planets are widespread throughout the Milky Way. The confirmation of a Borisov twin would transform a single data point into a trend, strengthening the argument that we live in a galaxy predisposed to create habitable worlds. Conversely, imagine if GB00810 had been interstellar, and its composition was wildly different from both Borisov and our own comets. That too would be a revolution. It would tell us that planetary systems form in a rich diversity of ways under different chemical and physical conditions. It would mean that the cosmic recipe book has far more variety than we ever imagined. Every single interstellar object is a precious free sample of another solar system. Each one we can study is a crucial pixel in the grand portrait of cosmic evolution we are slowly trying to piece together. The GB00810 event, the false alarm, sharpened our focus and our hunger. It was a powerful reminder of the stakes. We are on the cusp of a new era in this search, an era that will transform the trickle of interstellar visitors into a steady stream. This new age will be heralded by a machine of unprecedented power. High in the Chilean Andes on the summit of Cerro Pachon, the Vera Sea, Rubin Observatory is nearing completion. Its mission is called the Legacy Survey of Space and Time, or LSST. It is a monster. Its primary mirror is over 8 meters across. Its camera is the size of a small car, containing over 3 billion pixels of solid-state detectors. It will be the greatest data-gathering machine in the history of astronomy. Its goal is nothing short of creating a motion picture of the entire southern sky. Every 3 to 4 nights, it will image the whole visible cosmos from its vantage point, detecting billions of objects and meticulously tracking their motion and brightness. The sheer volume of data it will produce is difficult to describe. It will generate tens of terabytes of information every single night, a torrent of cosmic data that will require supercomputers to process. For the hunt for interstellar objects, the Rubin Observatory will be a game changer. It is projected to find not one or two, but dozens, perhaps even hundreds of interstellar visitors during its 10-year survey. We will finally have a proper statistical sample. We will see if Oumuamua-like objects are more common than Borisov-like ones. We will discover objects on approach trajectories, giving us precious lead time to organize follow-up observations with other telescopes, like the James Webb Space Telescope, to study their composition in exquisite detail. The days of frantic last-minute scrambles to observe a departing guest will be over. We will have a catalogue of visitors, a celestial immigration record. But even this revolution in detection is only the beginning. For some, simply watching these messengers fly by is not enough. The ultimate dream is to reach out and touch one. This is the goal of ambitious mission concepts like Project Lyra, a study by the Institute for Interstellar Studies. The idea is to design a spacecraft capable of a high-speed, rapid response interception of an interstellar object. The challenges are immense, bordering on science fiction. Interstellar objects are moving at incredible speeds relative to us. Catching up to one is not like docking with the International Space Station. It's like trying to jump onto a speeding bullet from another speeding bullet. The intercepting spacecraft would need to be launched with phenomenal velocity, requiring a massive rocket and perhaps a gravitational assist from Jupiter. Even more challenging is the reaction time. An object like Oumuamua was only spotted when it was already on its way out. A feasible intercept mission would require us to detect a visitor with years of warning, something only the Rubin Observatory might make possible. The probe itself would need to be a marvel of technology. It could be powered by advanced solar sails, vast ultra-thin membranes that use the pressure of sunlight for propulsion, or it might require more exotic technologies like nuclear thermal or nuclear electric propulsion to achieve the necessary speeds. The scientific payoff of such a mission would be incalculable. To fly alongside orbit, or even land a probe on an object from another star, would be one of the greatest achievements in the history of exploration. We could analyze its surface chemistry up close, drill into its interior to sample pristine material from its birth nebula, and study its structure and density. We could finally answer the riddles posed by Oumuamua. Is it a nitrogen iceberg, a fluffy fractal aggregate, or something far stranger? We would no longer be guessing about the nature of these travelers based on a few distant photons. We would be reading the history of another world written in ice and stone. So, the story of GB00810, the Faint Impostor, ends not with a conclusion but with a new beginning. It was a fleeting moment of excitement that quickly dissipated, a cosmic case of mistaken identity. Yet its legacy is profound. It was a fire drill for the entire astronomical community, a test of our ability to detect, track, and analyze a potential messenger from the stars. It revealed the subtle complexities of orbital mechanics at the edge of our solar system, forcing us to appreciate the strange mimicry of the Oort cloud's most distant children. And most importantly, it stoked the fires of our curiosity, reminding us that the universe is not a static, distant museum. It is a dynamic, interactive environment that is actively sending pieces of itself across the interstellar darkness from their home to ours. We are just now in this brief moment of human history, building the eyes to see them and dreaming of the hands to catch them. The interstellar puzzle deepens with every new observation, with every false alarm and every confirmed visitor. The questions echo in the vastness. How many are out there? What are they made of? What stories do they carry of the star systems they left behind? And do any of them tumbling silently through the cold void carry any sign that they are not in fact natural? We don't know the answers, but we are looking up. Our digital sentinels are watching, sifting through the light of a billion stars, waiting for the next faint smudge, the next anomaly, the next traveller to cross our threshold and beckon us towards a greater understanding of our place in the Feshalos. Cosmos, the quiet between the stars, is not empty. It is full of messengers, and we are at long last learning how to listen.